All right, this is our last video on VSEPR theory, and we're going to look at things with steric numbers of 6 or greater. Remember, as we build these, lone pairs repel more than bonded pairs, so they're going to want to go in the location that reduces the angles that those lone pairs are with each other. So we're looking at our chart again. We have, at this stage, filled in everything here and here and here, going all the way across steric number 4. We've also done steric number 5 with no lone pairs, with 1, with 2, with 3, but we said this isn't possible, so no steric number 5 with 4 lone pairs. And now we're going to look at steric number 6. All right, so let's take a look at this. Commonly occurs with elements that have 6 valence electrons in which their lone pairs are being broken up by highly electronegative atoms. So for instance, sulfur hexafluoride is going to contain 6 lone pairs. In this case, they are going to go out as a square along the central plane at 90-degree angles from each other, and then up and down. So all angles are 90 degrees, and they're going out in 6 directions in space. We say that this SF6 is octahedral, and the reason it's called octahedral is that if you were to connect all the dots, you end up with an 8-sided figure, an octahedron. And so there's 4 along the top, 1, 2, backside 3, and that side 4, and then at the bottom 1, 2, 3, and 4. So there's an 8-sided figure. Everything has 90-degree angles. The ax notation here, AX6. If we were to move over 1 on the periodic table to the halogen, let's say it was iodine or bromine, we could make 5 bonds and then maintain one of the lone pairs, and we would still have a steric number of 6. So we would have a ax notation of AX5E, and an example of this one would be bromine pentafluoride. We still have that lone pair at the bottom, so in this case we're going to put that as our lone pair in yellow. If we were to ignore the E, then what we could do is create a shape that looks like this. What do you think the name of this shape is? Best thing to do when you're thinking about naming the shape is connect the dots and think about, well, what shape does that look like? So we've got a square, because they're 90-degree angles, along the base, and then each of those goes up to the top. And what shape is that? This is what we call a square pyramidal. It's a square base, not a trigonal or a triangular base, but a square base with a pyramid coming off of it. In fact, the Egyptian pyramids were square pyramids. They had a square base and then they formed a pyramid. All right, let's take a look then if we move over 1 additional slot to the noble gases. So just as we can make XeF2 xenon difluoride, we can also make xenon tetrafluoride. So in this case, we would have 2 lone pairs and 4 bonds. So now we have our E on the top and the bottom. So let's get rid of those lone pairs and see what our shape would look like. We end up with something like this. All right, well, what shape is that? So if we connect our dots, what shape is that? Well, it's called square planar. It's a square that's on a plane. So pretty simple there, huh? Okay, so at this stage, we have created this part of our table. We can't go over to 3 lone pairs at steric number 6 because you can't go past the noble gas. So you're going to see a trend here, which is this is going across group 14, group 15, group 16. Then this would just be linear, so we can put in the, and then over here, we're going to go group 15, group 16, group 17, group 18, and then over here, group 16, group 17, group 18. So you can't do this, you can't do this, can't do this. All right, so we're filling in our chart. Okay, so just want to remind you of the rule of thumb when we're working with certain atoms that are going to become hypervalent. If there's an odd number of valence electrons, then that atom can only make odd numbers of bonds. So for instance, if we're looking at iodine as the central atom, we can have ICl, ICl3, ICl5, and ICl7 as we break up those different lone pairs. However, we can never have an even number for that. So you can't have P, which is an odd number of valence electrons, only bonding to 4 fluorines. The other rule of thumb is if you have an even number of valence electrons, you can only make an even number of bonds. So sulfur can make SF2, SF4, and SF6, but you can't have selenium with 5 fluorines because selenium has an even number. So let's see what you figured out by giving the steric number and shape for these 4 molecules. I want you to pause the video. I want you to draw each of the 4 with iodine as your central atom, so iodine's your A. The chlorine would be your X, and then you have to include any lone pairs that it has, the iodine has. What's the steric number, and what's the shape? Pause the video. Come back and let's see what you do. Okay, so iodine to chlorine, iodine would have 3 lone pairs and plus 1 bond to chlorine, so that would be linear. Iodine to 3 chlorines means 2 of the chlorines broke up a lone pair. So there are 2 lone pairs now and 3 bonds. That would put it at steric number 5. 2 lone pairs, 3 bonds. The 2 lone pairs would have to be on the plane, so that would be T-shaped. Iodine with 5 chlorines indicates another lone pair got broken up. So there's 5 bonds plus a lone pair, so that gives it steric number 6. But because one of the lone pairs is going to be ignored, we're going to end up with square pyramidal. Finally, iodine with 7 chlorines means 0 lone pairs going in 7 directions in space. We didn't cover steric number 7, but actually you can do that. Steric number 7 looks like this, in which you have 5 atoms along the plane, plus up and down. And in this case, we call this pentagonal pyramidal because it forms a pentagon on the plane plus a pyramid going up and a pyramid going down. So this is actually called pentagonal bipyramidal because there are 2 pyramids. I'm not going to test you on steric 7. I will only test you up to steric number 6, but I just want to show that does exist. So here is your pentagonal bipyramidal. All right, let's see if you can do SF2, SF4, and SF6. So pause the video and see what you come up with. All right, welcome back. Let's see what you got. So selenium has 2 lone pairs and can make 2 bonds. So because of that, you're going to have steric number 4, 2 lone pairs, 2 bonds. 2 of them are lone pairs, so that's going to result in a bent molecule that looks an awful lot like water does. Oh, H2O, SEF2, same exact shape. All right, selenium tetrafluoride has a situation in which one of its 2 lone pairs gets broken up to make 2 more bonds, so now it's going to have a steric number of 5, which is 4 bonds plus a lone pair. Well, if you have 4 bonds plus a lone pair, steric number 5, that's going to be seesaw. And finally, selenium with 6 fluorines means that all of the valence electrons are used up. There are no lone pairs. We're going to go 6 directions in space, steric number 6 with no lone pairs. That's going to be octahedral. All right. Determine what the steric number and number of lone pairs are on this molecule, xenon trioxide. If you can do this, you can do anything. So xenon has 8 valence electrons, 4 lone pairs. 3 oxygens are coming on, and we know that each oxygen wants to get 2 bonds. So essentially, each oxygen is going to use up each of the lone pairs. So we're going to end up with things going in 3 directions in space plus a lone pair left over. So it's going to be steric number 4, AX3E. So we're going to get something that looks like this, which is actually the same shape you'd expect from nitrogen with 3 hydrogens or ammonia, with the lone pair sticking up here. And since the lone pair is up here, we have trigonal pyramidal. By the way, here is XEF6. That has 1 lone pair, and then the 3 other lone pairs have all combined with fluorines. And we have pentagonal pyramidal, steric number 7.